Hello guys, welcome back. So far in our lecture series, we have talked about assumptions underlying the classical linear regression model. We have also talked about how to estimate the linear parameters, assuming all the assumptions of CLRM are satisfied. And one of the important theorems under classical linear regression model is Gauss-Markov theorem, which says that if all the assumptions of CLRM are satisfied, the estimators, those which are estimated through ordinary least square method, OLS method, they are best linear unbiased estimator. In short notation, they are called as blue estimator. Okay, so from now on, we'll talk about violations in the assumptions of linear regression model that we have, and we'll start with talking about heteroskedasticity in particular. So in today's class, we are going to talk about what exactly heteroskedasticity is, how do we detect the presence of heteroskedasticity, and what are the consequences of heteroskedasticity on the linear regression estimators. Okay, so heteroskedasticity, if you look at the term, so hetero refers to unequal and skedasticity is dispersion, right? So what exactly this term tells us? When we assume homoskedasticity in our linear regression model, so we see that variability in the error observations, and variability in most of the circumstances is measured by the term variance. So variability of the error observations, error terms across all the observations that we have included explicitly in the model, that is our data matrix, remain same or remain constant. So how do we write variance covariance matrix under the assumption of homoskedasticity? So we say that variance of error term ui conditioned on the data matrix is given as sigma square identity matrix of order n. So sigma square is a constant value. That's why this satisfies the assumption of homoskedasticity. So how do we write the problem of heteroskedasticity in statistical notation? So we say that variance of error term conditioned on the data matrix X is sigma I squared, where I goes from 1 to n. That is now no longer the sigma squared in this circumstances remains constant. So your variability or variance of u1 as sigma 1 square, variance of u2 as sigma 2 square, so on till variance of un given by sigma n square. And by the definition, sigma 1 square is not equal to sigma 2 square, and they are not equal to each other. Okay, so this is about the technical definition of heteroskedasticity. So by heteroskedasticity, what we mean or what we understand is that error observations do not have constant variance across all the observations in the model. In other words, non-constant error variance. So heteroskedasticity also refers to the phrase non-constant error variance. So you have to understand in this non-constant error variance. अब रही बात that how serious is the problem of heteroskedasticity? That is, we are trying to talk about the consequences of heteroskedasticity on the model that we have fitted. That is, if somehow we ignore that the model suffers from heteroskedasticity, what might be the possible consequences on the inference procedures or on the values of estimators that we have estimated using ordinary least square method. Okay, so having understood the technical definition of heteroskedasticity, let us now understand how do we detect the presence of heteroskedasticity. So एक सबसे simple method जो होता है to detect the presence of heteroskedasticity is to plot the residuals. So the first detection method is plotting the residuals. So either we plot the residuals against the fitted values of y that we have obtained using regression model, or we plot the residuals against any of the explanatory variables in the model to check whether we can identify a pattern in the values or among the values of residuals. If you are able to identify a pattern, that gives me an indication that your model might suffer from the problem of heteroskedasticity. And if you cannot identify a pattern, the model does not suffer from heteroskedasticity, is safer to assume for the time being. Okay. So plotting the residuals versus the fitted values or against any of the explanatory variables. So let us try to understand the graphical picture of heteroskedasticity first. So you have to understand that if the error variances are constant across each of the observations, it means as my explanatory variables change or as the values of explanatory variables change, there is no such change observed in the variance of residual term. So if I plot the residuals against any of the explanatory variables, or if I plot the residuals obtained from the regression line, we must get a spherical, or you can say no discernible pattern in the values of residuals. So what I mean by that, so if I plot the residuals, estimated residuals, so in case of homoskedastic error terms, my values must come something like this. In this case, we are not able to identify a given pattern in the values of residuals, and that's why we say that this is a homoskedastic error term. Homoskedastic error terms means the error has mean value 0 and it has a constant variance given by sigma square. Okay, in case of heteroskedastic variances, one of the typical type of heteroskedastic residuals will look like this. It can go either ways, that it starts with a greater variability, and as the value of x increases, the variability decreases. In this example, I have taken the case where the variability is lesser with the numerically smaller values of x, but as x assumes larger values, the variability observed in the residuals or estimated residuals is also large. So this is an indication of a heteroskedastic error observations. So what kind of data in which we can witness heteroskedastic error terms? So there are plentiful examples. Let me take certain very common example. So suppose we are trying to talk about expenditure pattern of given family or given household on their income level. That is, we are mostly trying to talk about cross-sectional analysis over here. We collect observations of expenditure pattern or expenditure amount and income for different households at different income level, and then we are trying to estimate a regression analysis out of that. So assumption of homoskedasticity, what it implies, if we are assuming that it satisfies the given data set that we have obtained, so it will imply that variability in the consumption expenditure remains same for a household or for a poor household which earns a lower value of income or lower income, and it will also remain same and equal to a rich household earning higher level of income. In other words, assumption of homoskedasticity in this case, in this example, consumption expenditure versus income, will mean that there is no variability in consumption expenditure in the households who belong to different levels of income. However, we must understand that this is a very unrealistic assumption to make, especially in cross-section data analysis. And that's why you will find that heteroskedasticity is commonly found in cross-section analysis. Second example, you can talk about if you want to talk about variations in profit earned by a given firm. So, assuming homoskedasticity means here is that profit or variance in profit earned by a firm of very large size is same and equal to that of variation observed in the profits earned by smaller firms, which is, you must understand, again a very unrealistic assumption to make. Nevertheless, if somehow we have detected the presence of heteroskedasticity, why should we concern ourselves? That is, what will be the impact of heteroskedastic error observations on the model that I fitted? That precisely is consequences of heteroskedasticity. So let us try to understand consequences of heteroskedasticity. And in the next class, we'll talk about the various tests of heteroskedasticity that we have. And in the next class, next class, we'll talk about remedial measures of heteroskedasticity. So all the violations related to heteroskedasticity, multicollinearity, and autocorrelation, we'll discuss each of such violations along three possible lines. So first will be detection, second will be consequences, and third will be remedial measures. So how do we detect the presence of violations? In this case, heteroskedasticity. What are the various tests available in various softwares? If we detect the presence of heteroskedasticity, why do we talk about heteroskedasticity or such violations? Is to talk about their consequences on OLS estimators. And once we have identified the presence, how we can apply measures which will lead to remedial, or you can say which will lead to remedying from such violations. Okay, so let us talk about consequences of heteroskedasticity today. In the next lecture, we'll talk about the detection tests that are available for heteroskedasticity. One of the most common example or one of the most common method is the graphical method, which we have already talked about, that you plot the estimated residuals obtained from the regression against either the fitted values or any of the explanatory variables present in the model and try to identify a pattern. Okay. So what are the consequences of heteroskedasticity? Is my OLS estimator still unbiased? Is it still consistent? And is it still efficient? So what we notice is that under the presence of heteroskedasticity, your OLS estimator still remains unbiased and consistent. Remember, consistency is a large sample probability. So this is a asymptotic property of estimator. So my OLS estimator, even under the presence of heteroskedastic error observations, remain unbiased. That is, expected value of beta hat is equal to true population parameter beta and it remains consistent. We'll talk about what exactly we mean by consistency, but for the time being, consistency applies here that its probability limit converges to 0 as n tends to infinity. Okay, so what exactly happens when you have heteroskedasticity? So in presence of heteroskedastic error observations, your OLS estimators no longer has or have minimum variance. So it loses the property of minimum variance and hence it becomes an inefficient estimator. Now, what do I mean by inefficient estimator? Means out of the class of all such linear estimators available, in the presence of heteroskedasticity, OLS estimator does not have minimum variance. Means there is another class of linear estimator which has smaller sample variance compared to OLS estimator. So consequences of heteroskedasticity is your OLS estimators remain unbiased and consistent, but they no longer have minimum variance, and that's why they lose the property of being the best estimator. So many times it is asked in multiple choice questions that in the presence of heteroskedasticity, does the OLS estimator remain best, remain linear, remain unbiased? So what you have to understand that in the presence or under the presence of heteroskedasticity, the OLS estimators remain unbiased, remain consistent, but they are no longer best or they are no longer the efficient estimators. And that's why we are concerned with fitting a model where the presence of heteroskedastic error observations are there. So this is the consequence of heteroskedasticity. In the next lecture, we'll talk about how do we detect the presence of heteroskedasticity. One method we have already talked about, that is graphical method. But there are other statistical softwares or statistical tests available, such as White's test, Bruce and Pagan test, Wolfray-Korn test. So then we talk about detection test, and after we discuss detection test, we go on to talk about remedial measures for heteroskedasticity.